So, Anderson's self-localization of light in pair plasma. This is the work I am doing with Viktor Gorayev from Colorado University, and he's actually a solid-state specialist. And when I talked about this it's the self-localization that gets the solid-state people most excited. Most importantly, this is a follow-up work to what we did with Kavli and Alexei, and our first paper is, I think, within hours of being finished and submitted, but this is an extension. So, super strong lasers in astrophysics. This has been discussed many times. Some horrible powers, A0 in the millions. Magnetic field may be dominant at the source and subdominant further out. 2 points that were not addressed, and I will stress it strongly, is that here we're dealing with pair plasma. And secondly, waves may start inside plasma and change their dynamics due to the slow evolution of the conditions. And this is very different from the usual laser experiment when laser is shot from outside. And my point is that this regime is mostly unexplored regime of laser plasma interactions, and there are interesting things, surprising things to be discovered. So, generally, there are two questions one can ask: generation and propagation, and I will start with propagation. Okay? So, what we know, and ... here is a little hint. So, here is our dispersion in plasma. We need omega larger than omega plasma, and we all reasonable people, and we think that in pair plasma we just write 2 and we are done. And there is also nonlinear solution here, Polovian. Basically, you go from gamma, you go from M to gamma M, where gamma is the effective Lorentz factor of the transverse motion. And you know, it's Russian plasma physics, 1950s, this must be right. And of course it is right. And sure enough, so here I am using epoch code, and I am looking at electron ion plasma with fixed ions, circularly polarized, highly underdense, and A0 just 10 to the minus 2. Basic linear, almost linear regime. And I'm not very good at making movies, and basically what you should see here is this pulse. It was traveling like this, and you can see nothing happens. And you know, it went to big depth, thousands of wavelengths. All good? Okay. Let's just then do it in electron-positron plasma. Same parameters, red is electron-positron. So again, we are highly underdense, weakly nonlinear. The electron, and here I am plotting the Poynting flux. Okay? And we see that, quite somewhat surprisingly, the little nose propagated, but most of the pulse in electron-positron plasma is reflected. We can look at the, again, zoom in on the Poynting flux in the back, and you see it is consistently negative. It is consistently negative, minus. And this pulse, again, propagated thousands of wavelengths. And what's happening, the little part, the first part propagates, but all the rest is reflected back. Okay? And here we are dealing with mesoscale phenomena, meaning this occurs on scales much larger than the microscopic scales, much larger than the wavelets, and yet much smaller than macroscopic phenomena. So the separation of scales doesn't work here. And I started doing pigs 2 months ago. My plots are ugly, but I think there is some beauty in their ugliness. So what we are looking here is a time snapshots of Poynting flux, and the pulse enters, and at first all is good. But then the tail starts to get, eaten out. And at this moment, you see, the negative Poynting flux is almost matching the peak Poynting flux. And again, the little nose propagates, but most of the pulse is reflected. Okay? And this, I interpret this results as Anderson's self-localization of electromagnetic waves in pair plasma. Now let's look at the lone pulse. Here I am plotting two things. Red is Poynting flux normalized to unity, and blue is density, or also normalized to unity. And what we see, first, the little nose propagates, as expected. But then there is a dark region. There is zero Poynting flux. Okay? Then we see large bursts of large negative flux, but that's, negative -1 means it's 2 times larger than the positive flux I am injecting. Okay? Then we see that the wave propagates, in this case, to a few thousand wavelengths, and no more. And this is a clear example of what people call Anderson localization, and I will explain it in more details. Also, we have huge density fluctuations. You see, we're dealing with weakly nonlinear, circularly polarized. You expect that density fluctuations would go as A0 squared, so 10 to the -4. While here, I have, I cut it off. They go further out, it all goes up to 10, and 10 to the -2. So huge density fluctuations. Okay? Interestingly enough, circular and linear behave similarly. So here again, at a Poynting flux, in blue is electron ion, circularly polarized, and linearly polarized, and not normalized, so it's 1/2. And you see that, again, for these parameters, it behaves as expected. While pair plasma, again, we see there is a dark region and localization here. Okay? And again, it's pretty deep, pretty deep. So what is Anderson localization? It's a very broad concept that generally refers to wave properties in random media. And at first, it was applied to conducted dielectric transmission, conducted dielectric transition. And roughly speaking, it's a diffusion with a phase. So it's not just particle running back and forth, but those particles also carry their phase with them. And Anderson got Nobel Prize for his work. Interestingly enough, the same year, Gerstenstein and Vasilyev showed that random dielectric reflects electromagnetic waves. And it's the same Gerstenstein who invented the LIGO concept. So that person obviously knew something about adding of phases of the waves. Briefly, in quantum mechanics, we all discussed this Dirac delta comma Kronig-Penny model, which is, Dirac delta comma is a set of equally spaced scatterers, and then you find that there are, Bloch states and conduction bands. Interestingly enough, if you, as a qualitative explanation, if you take out one pin, you will see that there will be a localized state. Okay? And actually, if you put random pins, all states will be localized in 1D. Localized meaning they don't extend to infinity. Okay, and in this case, okay. Then there is this quantum mechanical electromagnetism correspondence. Both operate with waves. Good. Of course, Schrödinger equation has first order time, but wave equation is second. But in a steady state, they look almost the same, with a subtle difference. So this is my randomly varying dielectric, and it comes with the wavelength, so with the wave vector, meaning the effects of this randomness are small at low frequencies. But of course, if you go to high frequencies, it's harder to keep coherence. So you expect that these effects operate in some range of frequencies. And actually, we know that fast radiative bursts are observed in a range of frequencies. And one can identify two effects of Anderson localization. First, a random dielectric reflects electromagnetic waves, and waves inside the electric become localized. So here is what happens. It's almost like a free electron laser. There is a weak back scattered wave that creates density sheets. And here, what I'm doing is just single particle trajectories in two counter-propagating waves. I show trajectories of particles for 2 periods, and you see that you generate 2 bunches per period. And then I do a phase diagram, so it's a single one particle approximation. And then I discussed this with Anatoly, and he quickly ran peak simulations, real peak simulations of pair plasma without initializing the counter-propagating wave. I was quite happy to see how similarly they look. So the main thing that happens is you form 2 density bunches per period. And those density are actually, in ideal case, they are logarithmically divergent, so they're very thin. But they're not steady, and as you can see from this picture, there is a bunch here, then here you may think that there would be more bunches per period. And here, snapshots again. So you have a density bunch, then this density bunch splits in 2, then those 2 run away, and a new one appears. So it's not simple 3-mode interaction. It's a bit messier. Yes. Oh, yeah. And importantly, if since you form these density bunches 2 per period, that corresponds to coherent backscattering, meaning the wave that passed through and got reflected here will add coherently with the wave reflected from this bunch. Okay. And then one can do a few more models. For example, here, what I do is the following. I have 1D layer, and then I put delta scatterers. And for each delta scatterer, it's delta scatter in terms of density. I can find the scattering matrix, and that scattering matrix acts on wave that is going forward, and that's the transmission coefficients, and this is the reflection coefficients. And then on the input there is 1, and on the exit there is transmission probability. And here is amplitude transmission, it's a small t, as a function of kind of the strength of scattering. It is of the order of unity until 1, and then suddenly, when you change just by a factor of few, the amplitude transmission probability drops by like 10 orders of magnitude. So the transmission probability, which will be squared, it will go as 10 to the minus 20. And that's, I think, I kind of reproduce the Anderson localization. One can also notice that, so this is only one run. This is not averaged. And one can notice when I go to small transmission probabilities, I have large fluctuations of the transmitted flux, and that's indeed what is expected in this regime in case of Anderson localization. Next, and that's something that I think we did something very unusual. Localization of waves already inside plasma. Imagine that there is a strong wave propagating a plasma, say launched somewhere. But then the properties of plasma change a little bit. And then we are going into the regime when under-self-localization occurs. So first what we do is we have this wave and we start growing random dielectric sheets. And then we're looking for normal modes. And indeed, so this is electric field as a function of coordinate. And this is a localized wave. You can think of it that here is an electromagnetically localized electromagnetic wave. Okay. Then I did something somewhat unusual. So I call it Klemov frame because maybe there is a better name. I learned it from Clement 73. So if we look at electromagnetic waves in unmagnetized plasma, they are superluminal, and omega squared minus k squared is Lorentz invariant. This quantity is A naught is Lorentz invariant, and plasma density as measured in the plasma frame is also Lorentz invariant. But we can go to a frame for the superluminal where K is 0, there is no magnetic field, and there is only electric field which is spatially constant and oscillating. And the current then is, the current compensates that electric field. And this approach effectively takes away the fast phase. Because normally when you deal with some modulations, you do slow evolution of the phase and you average over fast evolution of the phase. But here I take it out. In this frame, particles are moving, but actually in 1D you can factor out that parallel motion. And here is what I find. So in black, I have energy density of electromagnetic energy density. And you see that the waves broken up in bright spots and dark regions. And in blue is density, and you see that density inside is very small, while outside is large. And again, this is mild A naught. And here I am obviously in a nonlinear regime where Ponderomotive effects start to become dominant, meaning that the phase is not important at this nonlinear stage. Okay? Then what I do is I do a run, I print out my electromagnetic fields, and then I look for the maximum value of electromagnetic field in my whole domain. And then I plot it as a function of time. So I start with 1. And again, this is one run. This is, I wasn't trying to fine-tune this. This is one run, and you know, because you have localization, you concentrate electromagnetic energy in small part. Immediately I get to 4, and then I have a slow dissipation. Okay. And you can imagine that with better efforts and finer resolution, one can go to higher localization. Actually, there will be an example with higher localization. Let's move on. Temperature. Now I heat my plasma a little bit, and I see that little temperature kills this process, meaning little temperature makes my plasma transparent again. And what happens is, it's a parametric instability. So parametric instability starts with small seeds. But if you kill the small seeds, the parametric instability will never grow to large amplitudes. So small thermal spread kills the seeds of parametrically induced density fluctuations. Polarization. So here again, what I'm plotting in black is energy density. And in blue, I plot the position angle of the electric field localized there. And what you can see that within these bright spots, my position angle is constant. It's random, but it's constant. And I stress that this was produced by circularly polarized driver. The circularly polarized, well, it's in a special frame. There are perturbations that go counter to the initial wave. And when they grow nonlinear, the amplitude of this wave is, and of that wave is the same, and they add together, they become, give linear polarization, but it's random linear polarization in different, okay. And what I think has been previously mixed is the following. So usually, this looks like modulational instability, but I think it's not. Because usually modulation instability are, studied with Light-Hill criteria, and usually what's done is expansion in small a naught, and then you assume that evolution is slow and small density fluctuations, and actually circular polarized waves in pair plasma were proven to be modulation stable. But here it's different. Right away, if you remember, we get density fluctuations much larger than unity. And you can, if you do the little analysis, that you can show that the delta n over n diverges as kx squared. And then, of course, what the mode that we will win is, it would be of small kx, the largest of the small kx that goes nonlinear will win. So when we have these huge density fluctuations, in usual, so Gerstenstein, Vasiliev, they had fluctuations of the dielectric tensor, but here we can have density fluctuations so large that locally my laser may become, my plasma may become overdense. And that's clearly would be lead to wave localization. And in the end, it's all viable. If you have, you can think about, again, in this frame, you have a circularly polarized wave, electrons and positrons like that, or actually the better way would be they do it like this. So the velocities are always counterlined, so there is a current, and this current, there is a current flows like that, and that current likes to bunch. So it's all viable. And one more comment about the ponderomotive acceleration that Andrei discussed today. So without magnetic field, you expect gamma total to be 1 plus a squared over 2. Gamma z, well, okay, gamma, laser people use x, astrophysicists use z. So gamma parallel would be, oh, sorry, no. Gamma parallel is a naught, gamma perp is a naught, and you expect density. Density is actually interesting. It goes as gamma z squared. It's not a Lorentz transformation. It's gamma z squared. And in B field you can derive this. But here is an example: a naught 10 to the minus 1, and this is density. And you see, for this one, you expect one from the ponderomotive. You expect 1% increase, but here the increase is factor of 2. And what happens is that in pair plasma, and specifically in pair plasma, as it reflects the laser pulse, all the momentum is transferred to the plasma, and that's actually justifies my choice of a naught 10 to the minus 2, because if I go to a naught 10 to the minus 1, I start seeing large sweep-up effects, which would kind of mess up the interpretation. That's why I had to I had to go down in a naught. So, in some sense, I'm doing the simplest peak ever. It's 1D pair plasma weakly nonlinear, no guide field. And I find strange thing that electromagnetic waves cannot just propagate. And by just, I mean, just propagate. It's in cursive. They're reflected from the boundary. They experience localization if inside plasma. And of course, if you add a parallel guide field, it will make it more and more normal. It will kill this these effects, but it needs to be kind of, and of course I have runs with guide field. It will be interesting to confirm this instability it's specifically for pair plasma, because in pair plasma those density bunches are changed. It will be I cheated a little bit when I went to that frame, but it will be interesting to confirm it in the lab frame. I have a suspicion that even nonlinear subliminal alpha wave in pair plasma may be unstable. That will require a little bit subtle setup, and check out my, let's, if you're interested, I have a post to that kind of. And in terms of astrophysical applications, I think the result is too big to make a simple logical steps, hence this and that and that. One obvious thing is mildly strong wave may self-modulate into brighter pulses, and mildly strong wave may avoid absorption that we discussed today. But also this modulation may take a long time, and it may raise periodicity, and that may explain why we, if we are associated with a neutron star, but we still haven't identified, solidly identified a period. If I have 1 more minute, I will explain how to produce coherent emission. In 1 minute. Okay. So, there is a very simple way to produce coherent emission. So we had a few talks about shocks, and here is one way, 2 lines. All you need is a wave and a beam of electrons. That's enough. That's how FEL works. And that FL produces X-rays. So over 100 meters, it achieves phase coherence at the order of 10 to the minus 12. In this, I'm just conceptually, if you want to produce radio emission with shocks, first you have to put all your energy into the bulk motion. Then you have to stop that bulk motion. Then you have to thermalize that bulk motion, and then from that you hope to achieve some coherence. That's all you need in principle, just a beam and a wave. Of course, they should satisfy some conditions, some coherence. If they're all absolutely random, it won't work. But in principle, that's it. That's it. Okay.
For the very interesting talk. We have time for a couple of quick questions. Okay, Lauren.
Thank you, Maxim. I'm a little puzzled. I was just wondering whether you have checked the Lorentz invariance of your of the peak results, right? Because in principle you can have the plasma drifting, and you would like your results to be Lorentz invariant.
So this is a well-tested code. It's a standard code in laser physics. Actually, the results, when we were studying running it, the results was so counterintuitive that at some point I thought there must be a bug in that code. Yes, but Alexei probably comment on that. This is a well-tested code that has been used for at least a decade in laser research.
Any other questions?
What happens if you go epsilon above the mass ratio of 1? Like, at what point does it become electron ion plasma?
It's only me running and this code.
What do you expect? Like, is mass ratio of 2 going to change this conclusion and everything starts propagating, or you need to really have immobile ions?
In FEL, you also see you see the creation of these density bunches, but they're much shallower. So the densities with frozen ions, maybe I don't remember exact number, but you see density modulations with SRS, simulated random scattering, but those density modulations are much smaller because they are charged and they repulse and they stabilize. And you can actually do a simple estimate because for the trapped particles, the energy of the trapped particles, there is some tilde estimates that you can do in FAL when the FAL will reach the saturation regime.
Just quickly, what's set the minimum A0 to get this localization? Minimum A0.
Minimum A0.
Yeah, what set these things? Presumably, at some point, you should cover the linear.
Here, I am a little bit shaky on the principles of the peak simulations. If you are in a completely fluid regime, you don't expect any backscattering. Or in a completely fluid regime, backscattering is completely destructive and forward scattering completely coherent. And this would be more a question to peak specialists in how many particles per cell, how this would, I don't know. It's a valid question. I think it depends on the details of the simulations. But again, I am not a specialist.
Okay, I think let's thank Maxim again for the very interesting talk.